In last lecture, we have seen what is transition element. We have also seen the IUPAC definition of transition element and the electronic configuration of the first row transition element. In today's lecture, I am planning to give you something more physical and chemical properties of the first row transition metal. In particular, we are going to see the abundance and some of the general properties, density, ionization enthalpy, atomic and ionic radii, melting point and hardness, some of the reactions with water, and at the end of the lecture you will be introduced how electronegativities will vary in the first row transition metal ion. Let us first look about the abundance of this metal into the earth crust. The transition elements are widely distributed throughout the earth crust and in the ocean. The first 10 row element in the first row are making up total 6.79% of the earth crust. 3 of the transition metals are very abundant in the earth crust, among which the Fe is the 4th most abundant element found into the earth crust. Next comes the number of titanium, which is the 9th most abundant, and the manganese is the 12th most abundant element into the earth crust. Many of these are distributed widely into the nature. Scandium is the first transition element which is found into the electronic devices in +3 oxidation state. Titanium is equally important. We found titanium into the pigments in form of a hexa-aquo titanium complex, which is a purple color solution. Also, the vanadium, which is more useful in form of various vanadium alloy, is very important transition metal. It is also useful in the field of catalysis and possess a various oxidation states, which we are going to learn in the next lecture. Particularly the change in the oxidation states with the color. Chromium, which is the next very important element, is very hard, brittle and lustrous, and many of the time it is also possessing a color compound having variable oxidation state ranging from +2 to +6. As we know, the chromium +2, which we called it a chromous, is a bright blue in color and it is a powerful reducing agent, while chromium +3 is a dark green solid and the oxide of which when dissolves in water forms hexa-aquo chromium. In +6, that is hexavalent chromium, which is very much toxic and it is highly oxidizing in nature, particularly it occurs in a chromate and dichromate. Manganese is the next important transition metal having light pink in color in hexa-aquo compound, and the permanganate ion is highly deep purple in the color. All of us are aware with a KMnO4 potassium permanganate, which is a strong oxidizing agent. Iron, as we know, is the most abundant among all first row transition element, fairly soft, highly reactive, and hexa-aquo complex is a yellow color solution and quite acidic. Cobalt is the next important transition metal. Hexa-aquo compound is a rose colored and it is also important metal ion as far as the alloy formation is concerned. The next important metal is the nickel, which is also highly abundant and silvery white metal having very high electric and thermal conductivity. It is very much resistant to the corrosion and it is useful for the plating on the other metal. The hexa-aquo compound is green in color. The copper, which is the only perhaps the transition metal which is occurring in the 0 oxidation state after silver and gold. As we know, copper is also known as coinage metal. It is a part of many of the alloys, particularly brass and bronze, as we know. Along with the brass and bronze, it is also found into the sterling silver. Sometimes we know the terminology 24 karat gold and 18 karat gold. Pure 24 karat gold, all of you know, is not suitable for forming the ornaments, and therefore along with the gold some of the copper and silver is mixed into it. The meaning of 18 karat gold is 18 part by weight is a gold and remaining part, that is 6 part by weight, is copper and silver. Of course, the hydroxo aqua complex of copper can be blue as well as in green in color. The last element of the first row transition series is a zinc, which is a colorless, lustrous and very active metal. Most of the zinc compound is useful not only as a reducing agent, but also in the galvanizing the steel and other metal. After seeing the general properties of the first row transition element, let us now focus on the density of this metal ion. This table shows the densities of the transition metal ion along with the S block element at 20 degree centigrade. When you look to the figures, you will find that the densities of the D block metal ion is higher compared to S block elements. This is because compared to the S block element, the size of the D block element is smaller. Moreover, they are very closely packed because their crystal structure is either FCC or HCP. However, in the case of S block, that is alkali and alkaline earth metal, generally BCC structure is observed. Moreover, the relative atomic mass of this metal ion is also higher. So, these three reasons is mainly giving the high densities through the transition metal ion compared to the S block elements. The densities of the first row transition series is generally increases across the first series. This is because there is a decrease in atomic radius along the first series. Moreover, there will be increase in atomic mass across the series. So, this table again showing you the ionization enthalpies of the first row transition series element, and to compare this value with the sum of the S block element, the ionization enthalpy of potassium and calcium is also given. In this table, not only the first ionization enthalpy is mentioned, but the second, third and fourth successive ionization enthalpy is also mentioned. You will see that as we go from potassium to calcium, there is a sharp increase in the ionization enthalpy is observed. However, from calcium to scandium, there is a slight increase in the ionization enthalpy, and as we go from scandium to copper, also there is a very little change or slight increase in the ionization enthalpy of the elements is found. However, there is a sudden increase of the ionization enthalpy as we go from copper to zinc. The ionization enthalpy of the first transition series is generally greater than corresponding S block elements in the same period in the periodic table. This is because the atom of this D block element are smaller in size, and also the effective nuclear charge in these are greater compared to the S block element. Going across the first transition series, the nuclear charge of the element is increasing. Also, the additional electron is added into the inner 3D cell. Moreover, the screening effect of the additional 3D electron is also significant factor. The effective nuclear charge experienced by the 4s electron increases very slightly across the series. For the second, third and fourth ionization enthalpies, there is a slight and gradual increase across the series are observed. The first few successive ionization enthalpies for the D block elements do not show the dramatic changes, This is because the 4s and 3d energy levels are very close to each other. This chart shows the change or the variation of the ionization energies or ionization enthalpies of the first row transition metal ion. Particularly the first, second and third ionization enthalpy, as you can see, is gradually increases as we move from scandium to copper. In this, in addition to the third, the fourth ionization enthalpy is also included, and you can see that how ionization enthalpy changes as we move from scandium to zinc, and particularly the variation or trend in the fourth ionization enthalpy is worth to mention. Next very important property is the melting point and hardness. As we know that D block element is having very high melting point, and also they are harder compared to the S block element. The S block element are so soft that even some of the alkali metal you can cut it with the knife. Sodium is worth noting in this case. Both the 4s and 3d electron are involved in the formation of the metallic bond, and this is the reason why the melting point of this metal ion is very high. So, this figure shows the variation of the melting point as we go from scandium to zinc in the first transition series, and to compare with the S block, some of the melting point of the S block element are mentioned. Worth noting over here is you can see the potassium, which is very low melting compared to the other transition metal ion. Now, in this, the potassium has exceptionally small melting point because it has a more open BCC structure. When we see the trend in the melting point as we move from scandium to zinc, the unpaired electron are relatively more involved in the C of the electron, and these electrons are responsible for the changes in the melting point of this metal ion. Let us see how melting point changes as we go from scandium to vanadium. You will see that there is a gradual increase of melting point is found as we move from scandium to vanadium. This is because scandium has only one unpaired electron, titanium has a 2 unpaired electron, and vanadium has 3 unpaired electron in its electronic structure. And this is why this increase in the electron is responsible for the gradual increase of the melting point as we move from scandium to vanadium. However, as we move from iron to nickel, we will find there is a steady decrease in the melting point. This decrease in the melting point as we move from Fe to zinc is due to decrease in the number of unpaired electron. As we can see, there are 4 unpaired electron in iron, 3 in case of a cobalt, and only 2 in case of a nickel, and there is no unpaired electron in case of a zinc. However, in case of a chromium, there is a highest number of unpaired electron, 5, and still you can see that melting point is comparatively lower than the vanadium. This is because the electron in the half filled d subcell are relatively less involved in the C of the electron. Manganese also has exceptionally low melting point. This is because it has also having open cubic structure. The next important property is the hardness of this metal ion, which depends on the strength of the metallic bond, and the metallic bond of the D block element are stronger than those of the S block element. This is because they are much harder compared to the S block element. If we have a scale from 0 to 10 in which the 0 is assigned to the top and 10 is assigned to the diamond, then on this scale we can have various figures for the hardness for this first row transition elements. You can worth noting here is the hardest metal ion in the first row is the chromium, having the scale as near to the diamond, that is 9. However, the scandium and titanium is comparatively softer metal ion, copper as well, zinc is also a softer metal ion. As we know, the transition metal ion reacts very slowly with the water compared to the S block element. S block element, that is alkaline earth metal, reacts vigorously with water to form what we call metal hydroxides and also liberates the hydrogen. However, the D block elements reacts very slowly with the water and it will form mostly the oxides. However, reaction with the steam to give a metal oxides and hydrogen is possible in case of a first row transition metal ion. So, these are the some reactions of alkali and alkaline earth metal along with the transition metal ion with the water. As you can see that the potassium and sodium reacts violently with the water forming their hydroxides and liberates the hydrogen as well. Particularly sodium, you are well known that when it reacts with the water, sometimes blast may also occur. However, the transition metal ions such as zinc and iron reacts very slowly with the water to form their respective oxides. Apart from the water, the reactions of these metal ion with the acids are also known. These metal ion reacts very slowly with the acids to liberate the hydrogen and forms a corresponding salts, particularly when with HCl it will react, will form a chloride salts. The next important property of the transition metal ion is their atomic and ionic radii. Here two features is worth to mention, that the D block element have smaller atomic radii compared to the S block element and the atomic radii of the D block element do not show much variation across the series. So, this is how you can see the pictorially the variation in the atomic and ionic radii along with the charge states of the first row transition metal ion. This figure also shows the variation in the ionic radii along with the atomic radii. Ionic radii also changes in +2 as well as in +3 oxidation state. Here naturally the +3 oxidation state ionic radii will be smaller compared to the +2 oxidation state. This figure shows the comparison of the trends in the atomic radii of the first row transition metal ion with those of second and third row transition metal ion. Now, at the beginning of the series, as we know, the atomic number increases and therefore, effective nuclear charge will also increase and the electron cloud is get pulled closer to the nucleus and because of this the atomic size of the atom decreases. While in the middle of the series, there is a more electron enters into the inner 3D subcell. The inner 3D electron seals the outer 4s electron effectively and therefore, the effective nuclear charge is experienced by 4s electron increases very slowly. Only a slow decrease in the atomic radius in this region is found and at the end of the series, the screening and repulsive effect of the electron in the 3D subcell is become even more stronger and therefore, atomic size increases. So, this is what you can see that there are three regions. In the first region there is a slow decrease, in the middle region there is a almost no changes and in the third and the last region there is a small increase in the atomic radii is due to these two main factor, that is nuclear charge and the shielding effect of the d electron along with the 4s electron. So, this is how the atomic radii changes as we move from scandium to zinc. Same is the trend observed in case of the ionic radii with the +2 and +3 oxidation state. The next important property is the electronegativity of the transition metal ion. The electronegativity of the transition metal ion slowly increases, as you can see as we move from scandium to zinc, except for the last element in this series. Electronegativity is slightly increases down the column, which is opposite trend in this metal ion compared to the main group elements. This figure shows the trends in atomic radii, electronegativity and first ionization energy together in the case of first row transition metal ion along with some of the other member of the period 4 element. So, in summary, in this lecture we have seen the abundance and general property of the transition metal. Also, we have seen the variation in the densities, ionization enthalpy, atomic and ionic radii, melting point and hardness, and how reactivity of the transition metal with water and acid. And in the last, we have seen the variation in the electronegativity of the transition metal. In the next coming lecture, I am planning to tell you something more about the variation in the oxidation state and the variable oxidation state of the transition metal ion.